record. So good morning or good afternoon or good evening, everybody, wherever you might be. Today, hello. Yes, hello. Yeah. Today is my great pleasure and honor to introduce my collaborator, my friend and colleague, who is also running this seminar together with me, SØREN EILERS. And he will give us a user guide to the classification of graph-sister algebras, which is a wonderful topic, in my opinion. And we are all ears. The floor is yours, SØREN.
Okay,
take it away.
Okay, so before I start, I should probably mention that when everybody else was getting used to teaching on Zoom, I was on parental leave, so I'm sort of a newbie to all of this Zoom teaching. So I hope things work out, but I haven't really done it a lot. So the idea that, as Piotr said, the idea that I had for this talk was to say something about how you classify graph-sister algebras from a more sort of practical point of view, because we have some fairly nice and general theorems, but these theorems use invariants that are sort of forbidding. So the idea would be to somehow, since I'm imagining that some of you might be interested in trying to use these kinds of classification results in your research, which is not necessarily within the realm of classification. So I'm trying to sort of give you an idea of how we think in terms of classification, and then for the graph algebras, there are some easier things that you can do, and this is what I'm trying to explain. So this is my program. So I have a bit of a prologue to just put you in the right state of mind in order to talk about classification. So I want to say a few things about the Elliott program and how that sort of how I would like you to think about this. I'm not 100% sure that's the same way that George would like us to think about this, but I guess we'll find out. Then I'll mention the definitions of graph-sister algebras and the important properties, and this is sort of the introduction. Then the next two points, bullets 3 and 4, that's the user guide part. So that's the idea. Suppose you have a sister algebra and you want to know if it's a graph-sister algebra. If you want to know, suppose you have two and you want to know if they're the same, what can you do? And this is what I would like to spend most time on. So it has a matrix picture, which makes it easier to check these things, at least if you have a unitary graph algebra. And then if you don't, it's a little bit more complicated. And then at the end, supposing I have time, I would like to sort of put this into a bigger framework, because you can actually ask for isomorphisms in many different ways. It's very natural for graph algebras because they come with canonical structure, so that you might want to preserve. And then you could ask the question, not only are the sister algebras isomorphic, but are they isomorphic in a structure preserving setting? This is an extremely interesting problem, I think, but also a very hard problem, and I only have partial information. And this sort of comes through the idea of moves that I'm suppressing a bit. Many of you, I'm sure, have heard me talk about moves because I've talked a lot about moves, but they will come, and I cannot resist it, but they will come sort of later in the talk. Okay, so let's go back to the beginning of classification. I just want to point out a few things about the classification of AF algebras. And first of all, I want to point out that there's more than one classification theorem. That usually you don't perhaps think so much about that. But depending on what you're trying to obtain, there's various variations of the K groups that the ordered K groups that you need to use. So you can classify up to stable isomorphism, and then you need to do use just the ordered K0 groups, and also very importantly, I thought I changed that. That's actually the Efren Hadman-Shen is from 1980. They also proved they characterized the range of the invariant, and this turns out to be very important because it tells you if you have an object that you're hoping is perhaps inside the classifiable class, then at least you can look at the K-theory and see if it's possible that it has the right K-theory. So these, of course, these two results are extremely well known. The third result that I'm putting up here is less well known, but it actually says that if you have a stationary AF algebra, which means that it's a repeated system where it's easiest to describe the dimension group is that you just have the same matrix and you repeat that in your inductive limit. You can think of it as sort of a fractional expansion or something like that. And then it was proved by Bradley and Jorgensen with Kim and Rausch, who are famous symbolic dynamicists, that actually that's decidable. So there is an algorithm for if you have two of these matrices, there's an algorithm for figuring out if you get the same C-star algebra or not. And this, of course, is striking. Of course, it doesn't really make sense to ask if two general AF algebras are isomorphic because they will be given by some infinite amount of information. But suppose that the information is finite and repeated like this, then actually there is an algorithm. I should say that this is not a practical algorithm. There's no app or anything that you can sort of check this out, but at least it's known that there is a procedure to answer these questions.
Well,
so this is
this slide. May I interrupt
yes.
very briefly while you have this slide? I think that it should be borne in mind that the category of ordered groups that arises with the AF algebras, this is exactly the same category. Surprisingly, it's the same category as Bradley diagrams if you turn those into categories. So it really isn't a different classification from the Bradley one.
Right. Yes. I guess that should be said, and because I mean, so the strength of putting it into the, I mean, you could argue that for AF algebras, it doesn't really matter if you use Bradley diagrams or K0, whereas if you go to more general C-star algebras, it's definitely important.
Yeah, it's interesting that K0 is defined more generally. Yeah.
Yes, yes.
And as Larry Brown said to me once, there's also K1.
Yeah, yeah, I heard that story. And I think your answer was "so what," right? So.
Yeah. Well, okay, but he was just trying to help me because a month later he came out for showing that projections lift using Bott periodicity, and he knew that's what I was trying to prove.
I see. Okay. Okay, great. So so let me just point out that there's various ways that you can do classification of AF algebras. If you want them to be isomorphic, you need to throw in some more information, and usually that's done via the scale. That's just the collection of the elements in K0 that you get from the projections in the C-star algebra themselves. And actually, there's also a range result that shows that you can have any reasonable scale. Oh, there, I changed the year. And you can also, if you have a unital AF algebra, then you can just, instead of the scale, you can use the class of the unit. And you have sort of also a range result saying that these are all the possible dimension groups with order unit is what you get. As far as I know, there are no decidability results here, but I'm not 100% sure. So of course, this is the starting point of classification. And then there's sort of the Elliott programs. So I'm putting here the old form of the Elliott program was that very sort of ambitiously, we look at all simple separable nuclear C-star algebras, and then we have a bunch of data which is known to be invariant. So it's K0, K1. I don't really need the details of this. So if you don't already know it, it's not going to be important. You have the trace space and a certain map making things fit together. And then in the beginning of the Elliott program, it was hoped that, in fact, this would work for all simple separable nuclear C-star algebras. After around 2000, examples were known by Toms and by Radam showing that this would not work.
Sorry,
so,
there is a question.
Yes?
Do you mean just NSS or NUSS? Do you assume unital or not?
Here, I wouldn't need a... that's a little bit up for debate. I think probably it should be unital or stabilization of something unital. So probably that's a fine point here. That so maybe I should have been a little bit more careful here.
It already says up to stable isomorphism.
It says up to stable isomorphism, yeah, but I don't know if it has to be stably isomorphic to something with a unit, which might be a problem. But the point I want to make here is that in the early days of classification, most C-star algebras considered were inductive limits of nice C-star algebras, building blocks, and George showed that in fact all of these reasonable Elliott invariants could be realized by inductive limit C-star algebras, right? And so at the time you could only classify those, but this actually turns out to be an extremely important observation, because at the end of the day, when you have a better classification result, and you also know that the invariant is realized by the nice C-star algebras that you studied in the beginning, then actually you've proved that all the C-star algebras are isomorphic to a nice C-star algebra. So this is, when I go to the next pass, this is sort of, we're looking for find and describe. I'm very vague here, so sorry, George. We find and describe a large class of C-star algebras. I put T and W for Tom's Winter, that work, right? So that you actually do get a complete invariant up to stable isomorphism. And what happens is that it seems to be the case, I don't think that's a theorem, it's more like a principle, that whenever you have a C-star algebra in the classifiable class, when you then look at its K-theory, it's some K-theory that, well, it's Elliott invariant, it's some Elliott invariant that you could realize with a nicer C-star algebra, which is an inductive limit, and then you actually prove that this C-star algebra is an inductive limit up to isomorphism. But of course, you don't know this a priori, so it's very important that you have these stronger classification results that say that if you have a C-star algebra that you want to study, it falls in the classifiable class in the stronger sense. So that's why these steps in the sort of revised Elliott program are very important, even though at the end of the day, the C-star algebras are in fact the ones that we knew already. But now we have the kind of results that allow us to say that whenever you have interesting C-star algebras like cross products with very modest conditions, they will end up in the classifiable class without you having to say anything more. So this is somehow a philosophical remark that I want to take with me to the discussion of the graph algebras. So now you can sort of ask the next question. Suppose that you have, in the AF classification result, there was no mentioning of simplicity. That's not necessary. So since you can notice that, you know, we can classify AF algebras without asking for simplicity, then can we carry over the program to non-simple C-star algebras? That's a little bit naive, because the K-theory of an AF algebra knows the ideal lattice of the C-star algebra, and that's not generally true. So that's a bit too much to ask for. But of course, with the Elliott program almost completed, there's a little snag with the UCT and these kinds of things. Then of course we're interested in the more general setting of non-simple C-star algebras, and that is going to be very difficult, right? I mean, first of all, when you look at the classification of simple C-star algebras, you can sort of put things in types. You have the stably finite ones and the purely infinite ones, and so you can deal with them separately. If you have a non-simple C-star algebra, it's probably going to be built together in general by things that are, some of them are stably finite, some of the simple subquotients are stably finite, some of them are purely infinite. So you have to wonder how you deal with this kind of mixture of C-star algebras, and I don't know how that's done, but it's a good test case to look at the graph C-star algebras. And this, I think, was the motivation for most of the people who have done classification of graph C-star algebras, is somehow to understand what are the limitations of going to the non-simple case. But it actually turns out to be useful for other purposes. And this is what I'm trying to sell here today. Okay, so what is a graph C-star algebra? So first of all, what's a graph? I would like you to think of a graph as a quadruple. So it has two sets, E0 and E1, and then there's two maps, R and S for range and source. And then we think of an element in E1 as an edge that goes from S of E to R of E. You can also draw graphs like I did here, or you can think of them as adjacency matrices. It's going to be very important in this talk that if you have a graph with finitely many vertices, then you can describe everything in a finite matrix. Of course, that matrix may contain the simple infinity. So what this double-headed arrow means that there's infinitely many edges that go from the leftmost vertex to the next one. And I just put in, yes?
May I ask you just a very naive question? I always have such situations with infinitely many edges pointing in one direction, but this is always countable. Does anybody use a situation where you have the infinities in a graph which are bigger than countable?
Well, the definition makes sense.
Exactly.
But you'll get a non-separable C-star algebra.
Yes.
And I think for classification purposes, I don't think that has been studied at all. Mm-hmm. So, but I've actually thought about this because you could definitely make sense of taking various, infinities and put that in a matrix somehow. Mm-hmm. But I don't know how hard it would be.
All right.
So in a second, I'll make everything countable.
Okay,
but that's all the definitions are going to make sense without that. They may not be so interesting. But actually, there are some examples. There's this old question of the difference between prime and primitive C-star algebras, and there are counterexamples that have been found in graph algebras that are non-separable in this kind of. So you can. It's sort of useful.
Okay.
This point of view, but not very developed, I think.
Okay, thank you so much.
And then, so we need to talk about regular and singular vertices. This sort of goes into the definition I'm going to show you in a second. So we say that a vertex is a sinc if it emits nothing, and it's an infinite emitter if it emits infinitely many edges. And those are sort of problematic for the definition. There's a choice of a direction, and there's two conventions that are used. So unfortunately, there's a little bit of a confusion here. I'm using the so-called Northern Convention because in my country, the cars drive on the right side of the road, which is the customary thing to use that convention then. But you can do it the other way around. But there's a lack of symmetry here. So if you can also talk about sources and these infinite receivers, and they're not a problem for me in the same level as the other kinds of vertices. The ones that are sincs or infinite emitters, I will call them singular, and the ones that are not, I'll call them regular. And the singular ones, when I remember, they will be white if I draw them, and the regular ones are black when I draw them. And now, I mean, this is always a little bit silly when you do this in a talk. So this is the definition of a graph C-star algebra. And the thing is that, if you've seen it before, then you don't want to see it again. And if you haven't seen it before, then it takes so long to absorb it that I'll be gone from that slide before you've sort of read it. So I apologize for this, but so the way that it's set up is that you take
what's that? Hello?
So what you do is that you take one projection for each vertex in your graph, you take one partial isometry for each edge in your graph, and then you put in some relations that are called the Kunz-Krieger relations for reasons that I'll explain in a second, that somehow says that if you look at the initial projection of the partial isometry, that corresponds to the projection of the range of that edge. The final projection is dominated by the projection of the source. And then when you add up the final projections for the edges that start in some vertex, that should give you the projections corresponding to that vertex. And this sum only makes sense if you have a finite number of such edges, right? If it's a zero, if it's an empty set, that sum doesn't really make sense. If it's an infinite set, then you would have to talk about some sort of convergence, and this is problematic. So this is why we only have this relation put in for the regular vertices. And then an important observation is that the graph C-star algebra is going to be unital precisely if there's finitely many vertices in the graph.
Sorry,
So,
just very quickly, if I might cut in.
Absolutely.
Because you see, this condition number 2 can have a very nice algebraic presentation. I mean, of course, it's customary to write it this way, but you can write it the equivalent way, which is sort of along the ways of path algebraic thinking. And it's completely equivalent.
Yeah, so like it's dominating that one
you
is
can write
the
it as
unit
an
for
equation instead of, you know, inequality, which for pure algebras is daunting.
That's a good point. I mean, for C-star algebras, this is a natural thing, but it looks a little bit weird if you're trying to do it in a more general sense, which actually is done. I mean, so I'm not going to talk about Levitt path algebras and so on, but you can make sense of these things in a completely algebraic setting.
Exactly. Yes. Mm-hmm.
That's a good point. So here's a thing that I need to really make sure to not talk so much about symbolic dynamics, because that would just take too long. But this is extremely important for all that I'm doing. So let me just spend a little bit of time on it. So I'm sure you've all heard of the Kunz-Krieger algebras, and I want to point out that they are special cases of graph algebras. And the way that they are special cases is that the graphs that you want to think about will be finite, so finitely many vertices, finitely many edges, and sinks and sources should be forbidden. The point is, if you have a graph like this, which is, you have no stranded vertices, right? So this means that if there's no sinks, you can always sort of move on from a vertex. If there's no sources, you can always move into a vertex. So it makes sense to look at the doubly infinite paths that you get from running around on such a graph. And this is a so-called shift of finite type, an important class of symbolic dynamical systems. And when Kunz and Krieger made the definition of the Kunz-Krieger algebras, they wanted to understand the, I hope I'm not putting things in your mouth. So they wanted to understand the relations between the dynamical systems and the C-star algebras. And these were recognized in the first papers, various notions like if you're saying if the dynamical systems are identical in this sense, then the C-star algebras are identical in this sense. These relations between symbolic dynamics and the so-called Williams problem that has to do with the difference between being shift equivalent and strong shift equivalent are extremely important for all that I do. But I'm sort of suppressing in this talk because it would take too long to explain the relation here. So it's probably going to be clear to those of you who know symbolic dynamics that these things that are standard in symbolic dynamics have been imported in the things that we do, and the many things that somehow when we can make things work, it's usually because we're importing some deep insight from symbolic dynamics, but it will not be super clear in the talk here. So I apologize for that, but I have to. I could talk about this side of it for hours because I mean it's my favorite subject. But if that doesn't help you if you want to answer questions about concrete graph algebra. So let's move on. So here are some examples. So I will just, this is an ad hoc notation. So GC star is a class of graph C-star algebras where E is a C-star E, where E is a graph. And here's some basic examples. You can get the complex numbers, the 2x2 matrices, the Kunz algebra O2, the Kunz algebra O infinity. They are just very easy examples from, you can just read off the generators and relations. You can also get the circle algebra by just having a single source, because then you get the unit, I mean, these are universal C-star algebras that describe the universal property of a unitary. You can have the triplet algebra. You can look at the unitization of the compacts. you cannot do the UHF algebra as a graph algebra because it's unital. And if you want to represent a unital C-star algebra as a graph algebra, then you're going to have to use a finite graph, and that's impossible. But you can get the stabilized UHF algebra by the graph that I drew there. Mm-hmm. So lots of C-star algebras turn out to be graph C-star algebras for more or less obvious reasons. And the idea of this talk is that you may somehow run into a C-star algebra that happens to be a graph algebra, and then we may be able to say something about the classification of these objects. So that's the philosophy here. I need a little bit more background, so let me do this relatively fast. So there's something called a gauge action on a...
Sorry, just a second. Yes. There's a question from the audience. Yes. Can general Excel-Laka algebras capture UHF algebras?
I don't know. I don't know.
Exactly.
Yes.
Yeah,
you know,
like,
Alex?
So, no, I mean, like, so I thought it maybe from somebody here knows about something.
Yeah, I'm not so familiar with Excel-Laka.
Like Marcelo?
Yeah, because Marcelo, I think, is in the audience, yes.
Oh.
Marcelo, you are muted.
Yeah, I think for the same reason, it's probably not, but I have to think about it. I don't think we should hang up with this one.
Okay, let's move on.
Okay, yeah, well, but good to see you, Marcelo. So, okay, so whenever you have a graph algebra, it comes with an action of the circle in a very natural way. You just put a phase transition on the partial isometries. And then just because all the relations that I had that involve the SEs have the form either SE star SE or SE SE star, these sets will cancel out. And so it's very easy to see from the universal property that you get an action which is a star automorphism on any graph C-star algebra. This goes back to the Kunst-Krieger algebras where it played an important role. There's also a diagonal, which is the span of S alpha star, where S alpha is a path. So you just take a path of edges and you take the corresponding partial isometries, you multiply them together. And if you sort of do it in this balanced way, this C-star algebra will be commutative. And it has, in the Kunst-Krieger case, its spectrum is precisely this shift of finite type that I described before. So this is these are natural objects. And this is what I'm talking about when I'm getting to the idea of having natural isomorphism that also preserve underlying structure.
And am I right to assume that for you a path is a finite path?
Yes, finite path. Thank you. So a little bit about K-theory. So K-theory is easy to compute for graph algebras. This is one of the main nice features of them. So what you need to do is that you look at the adjacency matrix, and then you need to sort of take the adjacency matrix and clean it up a little bit. First, you have to subtract the identity. So you subtract you subtract ones down the diagonal. And then actually to compute the K-theory, you need to remove all the rows that come from singular vertices, and you also actually should remove columns that are come from sources. So you can sort of clean up the matrix a little bit, and then you transpose it. And then the theorem says that, I mean, these are sort of classical results. It says that K0 and K1 are the co-kernel and kernel of these matrices. So that's sort of the little dot is supposed to remind you that this is the regular part of the adjacency matrix. Of course, if you have an infinite emitter, you're going to have to worry about what is the co-kernel of something with infinite multiplicity. We're just going to delete it, so it's not going to play a role. And to compute the class of the unit, you have to keep track of the information that lives on the sources. So this is sometimes you would rather not do that because you're trying to do stable isomorphism. Sometimes you want to keep this information. I'll come back to that in a second. You can also describe the gauge invariant ideals of these C-star algebras, they correspond to certain hereditary subsets, and it turns out that these ideals and the quotients that you get by modding out by them are themselves graph C-star algebras. So this is a nice sort of closed class of C-star algebras.
It's funny, Søren, because I just got this question in my class about graphs, whether an idea like this is itself a graph C-star algebra, and you just gave an answer. So,
yeah, I mean, the thing, I'm glossing over something complicated here, because the ideal, if you have this hereditary saturated subset, then the ideal is going to be stably isomorphic to the graph algebra of that subgraph.
But stably isomorphic, not isomorphic.
But actually, there's a theorem due to Hong and Szymanski that says that it actually is on the nose isomorphic to a graph C-star algebra. You just have to change the graph, and there's a procedure for doing this. Okay. So all of this makes sense.
But it's not an obvious thing. I mean, it's
no. This is
because I couldn't answer it in my class.
Oh, that's perfectly reasonable. So returning now to classification, right? So if I have a graph C-star algebra, which is also a nuclear in this sort of naive classification class, with I'm asking for nuclearity, separability, and simplicity, this will fall in the classifiable class of the Elliott program. So all graph algebras are nuclear, they satisfy the UCT. As we discussed already, it's going to be separable if and only if the graph is countable. And there is a dichotomy result, which sort of goes back to the beginning of the theory, that says if you have a simple graph algebra, either it's AF or it's purely infinite. So either you're in the classification result, you're sort of covered in the simple case by George's result or by the Kirchberg-Phillips result. So you have very general classification results for simple graph algebras. And actually, if you want, I mean, the next two lines are a little bit silly, but I'm just saying here that so that's like, I can take all the graph algebras and put them in two piles, and both piles are classified. But actually, we can classify them together because the K-theory will tell us which class we're in. Essentially, just because the ordered K0 will tell us, I mean, if everything is positive, then we're in the purely infinite case. And if something is not positive, then we're not in the purely infinite case. So you can do all this with this simple-minded invariant in the simple case. But now, what happens more generally? So I think we're coming up on 40 years of classification for the Kunst-Krieger algebra. So there's this paper by Enomoto, Fuji, and Watatani is pretty old. They sort of sat down and started to classify Kunst-Krieger algebras based on various graphs by sort of ad hoc methods of looking at K-theory and something slightly more complicated. They didn't get very far, but because they didn't have a lot of machinery. But this, I think, is the beginning of trying to classify the Kunst-Krieger algebras. And then these are sort of the main events. So in 1995, Michael Röder classified the simple Kunst-Krieger algebras. So he did this by appealing to some deep observations by Kunst and Krieger that said that essentially the notion of flow equivalence of the underlying shift spaces was very close to isomorphism of the C-star algebras, but there sort of was a difference, and Michael proved that this difference was not detected by the C-star algebras. So the defect, if you like, between flow equivalence and isomorphism of C-star algebras, this was somehow resolved in this work of Röder. This is before the Kirchberg-Phillips result, and I'm pretty sure that it was a major point of inspiration for the Kirchberg-Phillips program. But when you have the general Kirchberg-Phillips result that says that you can classify as purely infinite nuclear C-star algebras, then that follows as a special case of that, but it came before. And Röder actually also classified Kunst-Krieger algebras with one ideal, so not just the simple ones. And then Gunnar Resthoff, who was then my student, could do all the finitely many ideals. And I, a little bit accidentally, did the first classification result with Mark Tomford on trying to classify non-simple graph C-star algebra. We could only do the unique ideal case, so we didn't get very far. And this was only stably isomorphic. So if you want to do classification of these kinds of C-star algebras, the kind of invariant that presents itself is a little bit ugly. And this is precisely what I want to talk you out of using that. So that's the second part of the user manual idea, that this is a complicated invariant to use, but it's very easy to explain. So suppose I have a C-star algebra that has only finitely many ideals. Then whenever I have a chain of ideals I in J in K, I can do a short exact sequence of, these are sort of Noether's isomorphism theorems, and then I apply the 6-term exact sequence in K theory to that, and I get a bunch of 6-term exact sequences. So very naively, I just take all the 6-term exact sequences that I can get out of my finitely many ideals. And I call that the filtered K theory. It's important to note that the maps are part of the invariant, right? So the maps that I have in the 6-term exact sequence, these are part of the invariant. So this means that if I have 2 of these invariants and I'm asking if they're isomorphic, I have to find a set of isomorphisms that commute with these given maps. So this, of course, makes it complicated to check these things. And so this is not a very practical invariant. It was actually discovered first in the setting of shift of finite type in work of Euler and Huang, and they called it the K-web, which is perhaps a more sort of saying name about how do you deal with it. But the point is that you can very easily put order on that, because you just take the K0 groups and they will have some order, and then this is the ordered filtered K theory. And you can also put a scale on in the K0 groups, if just like we saw in the AF case. So this all makes sense. It's just not so easy to deal with. So
this what is the scale? What is a scale? So
the scale is what you need to do if you want to have an on-the-nose isomorphism, not just a stable isomorphism, but an honest star isomorphism. Then you somehow need to keep track of the size of the matrices that you're dealing with. And, and the one way of doing this, which is the most general way, is that you just take all the elements inside the K0 group that can be represented by projections in the C-star algebra itself, not in the matrices over the C-star algebra, as you would do in the construction of K0. So scale is usually something that's a little bit complicated to compute, but it sort of makes sense, and it would have to be preserved by an on-the-nose isomorphism. So that's that we just throw that in if you like.
Okay, thank you.
So a long time ago, we made this working conjecture. We actually might as well come clean about this. We put this in a fairly obscure paper in the Malaysian Math Society. We somehow thought that if this is wrong, nobody will notice. And if it's right, then we can say, oh, we put that in the literature. So the jury is still out on that, interestingly. I mean, we worked very hard on this, not recently, but we could prove it in the one primitive ideal case, and we could actually also prove it. I mean, what I mean by one primitive, I mean, if you have a unique ideal in the C-star algebra, then you have 2 points in the primitive ideal space. So that's one step up from being simple. We could do that. If we have 3 points, then we could almost do that, but we had to ask the K groups were all finitely generated. Essentially, if you know about these things, it's because we go via KL, and that is only the same as KK if you have this kind of condition. But even if I have 4 points in my primitive ideal space, it's just wide open. And the problem is that we have this mixture of things that are AF with things that are purely infinite. And if you sort of try to do the sort of a bootstrap approach to this, which was invented by Rördam, and you sort of get stuck in this, and we weren't able to get very far on this. So I'm trying to reinvigorate this program a little bit and see if maybe we can do more. But at the moment, I would have to say that this is not so promising. And actually, recently we found out that this idea of putting a scale doesn't even work with two ideals. So there's counterexamples in, this is studied by a work of Gabe and Ruiz, where they find C-star algebras that are not isomorphic. They will be stably isomorphic, but not on the nose isomorphic, even though they have the same scale. So there's some complications here that are just daunting in various settings. So this means, and this is sort of the bad news, is suppose you have general graph algebras, then we don't know so much about classification of the non-simple ones here. So that's the bad news. What you can sort of try to change, you can sort of try to change the rules a little bit, and then say, let's assume now that there's only, I will make it slightly more general. I will ask for only finitely many gauge invariant ideals. So, I mean, some ideals are going to be gauge invariant and some are not. Now there can be infinitely many non-gauge invariant ideals, but I'm asking for only finitely many gauge invariant ideals. That's automatic if you have a unital graph algebra. And then I just look at only the 6-term exact sequence that come from gauge invariant extension. So we call this the gauge filtered K-theory. And we can put order on in the same sense as before. This is something that is very easy to compute based on the graph if the graph is not too big. And actually, if there's only finitely many ideals, as I did in the first slide, then you can prove that all the ideals are gauge invariant. So the kind of problem that you're looking into is something like having a circle, like in one of the examples I showed you. And then we have this very satisfactory result for classification for the unital graph algebras, right? So I'm asking now for the C-star algebra to be unital. So that's the same as asking that there's only finitely many vertices. There might still be infinitely many, countably infinitely many edges. And then we prove that this gauge filtered ordered K-theory is a complete invariant. And we also have, so this is for stable isomorphism. We also have an on the nose result. Since we have a unit by assumption, we don't have to deal with the scale. We can just look at the class of the unit. So we just put that in. And then that turns out to be a complete invariant also for on the nose isomorphism of unital graph algebras.
Oh, Eric.
And then the next thing is that we know the ranges. This is work of Arklint. And we also know that actually these are decidable properties, because you can translate this into something that's been studied in symbolic dynamics by Boyle, and a recent paper by Boyle and Steinberg that prove that this is decidable. So you can actually, there's a theorem saying that there is an algorithm for checking these kinds of things. Unfortunately, this goes via the famous algorithm A of Grünewald and Siegel, which is a sort of, this comes from geometric group theory, no, arithmetic group theory, sorry. And this is sort of famously non-practical. So the fact that there is an algorithm unfortunately doesn't give me a program that I can run. I mean, so there's no app for answering these kinds of questions, but we know that it's decidable. So I'm very proud of this result, but I have to admit that it's not very practical. So if you have a C-star algebra with a bunch of ideals, more than one, then I don't think you want to compute this filtered ordered K-theory and figure out if they are isomorphic in various ways. So you have to somehow go another way, and this is what I would like to show you now. Okay, so now a few words about the limitations of this, right? Because I mean, the whole idea of this business is that we have a nice classification theory for graph C-star algebras, And then we also have the observation that graph Caesar algebras seem to turn up in lots of settings. So there seems to be some sort of tendency that if you have Caesar algebras that look a little bit like a graph algebra, then they actually are graph algebras. And this is somehow, this happens very often with the, even if you go back to the Kunz algebra, right? There's many ways of describing O2 that maybe doesn't look like O2 a priori, but it turns out to be isomorphic to O2. And then this is sort of a generalization of this property. But there's various things that would have to be true. So if you're sitting now, if you have a concrete example in mind and you're wondering, this Caesar algebra that I care about, is it a graph Caesar algebra? Here's a bunch of things that would have to satisfy. First of all, it's always nuclear. So if you have something that's not nuclear, then you're out of luck. There's variations of the graph algebra definitions that will give you some non-nuclear Caesar algebras, but they don't have a nice classification result theory, as you can imagine. Another thing is that K1 has to be free. It's the kernel of a certain map, so that's why it's going to be free. If there's only finitely many ideals, then the real rank has to be 0. And actually, every simple subquotient is going to be a graph algebra, so it's either AF or purely infinite with free K1. So you can sort of, there's various things that can go wrong. If you don't have finitely many ideals, then, but let's say you have a unit, then it's slightly different. So now you can have infinitely many ideas. You could, for instance, you can have a circle algebra, then still it has to be nuclear, K1 has to be free. And if you have a nuclear graph algebra, then there's a rule that says that the rank of the K1 has to be less than the rank of the K0. This has to do with this kernel co-kernel description that means that the kernel has to be smaller than it's a kernel or co-kernel of a certain rectangular matrix. Remember, I deleted some rows and then I transposed, and this is where this comes from. You can actually also
this fact that K1 of A is free. That's just a very simple observation, right? That
yes.
Every subgroup of a free abelian group is
exactly.
a free abelian group.
Exactly. Yes.
Okay.
And this is somehow, this is a major restriction, right? Because there's many. I mean, this is probably the biggest problem, and this has also been a key motivation in looking at more general kinds of graph algebras like higher rank and various topological graphs and so on, is ways of getting with something that looks like the same definition. You can
correspondences, perhaps, right?
Exactly. So various ways of getting K-theory that is not necessarily free in K1. But this is all, again, you know, if you go in, so there's various ways of generalizing the idea of a graph algebra, but it's only for the graph algebras at this time that we have these very strong classification results. Of course, you might hope for the future, but that's hard. But if you have a unital graph algebra, then actually the primitive ideal space is going to have to look fairly special. So it's going to be, if you have only finitely many ideals altogether, then the primitive ideal space is going to be an Alexandrov space. It's like an ordered topology, it's very highly non-Hausdorff. But then if you have circles, then you can sort of take a point in that space and you glue in a circle where that point sat. So you will still have a very sort of non-Hausdorff thing, but you have these standard circles sitting inside where you used to have points. So this is sort of, you can sort of see if you can compute the primitive ideal space, it's going to have to look like that. You can live with circles, but that's the only sort of one-dimensional space that you would accept. And then, as in the other case, when you have let's say an infinite dimensional simple subquotient, it has to be either the compacts or purely infinite with free K1. And here I might as well come clean again. This is the big problem of working only with unital graph algebras, and probably also why, I mean, the proof that we have is completely different from the general machinery that I showed you, but probably that's also why we can make it work, is that we avoid most of the AF algebras here, because the only AF algebras that you can get inside the unitary graph algebras are the compacts or extensions of compacts. So we're not seeing the full force of the Elliott classification for AF algebras here. And the problem has to do with, it's a well-known problem in classification. It has to do with the corona algebra of an AF algebra is not necessarily simple. It is for the compacts, but you run into some of these sort of fullness issues that we don't know how to resolve them at the moment.
Sorry, can you remind us what corona algebra is?
Yeah, so you take the multiply. You have a non-unitary C-star algebra. You take the multiply algebra and you mod out by the original.
That's what I thought, but I wanted to make sure.
Yeah, I guess that's an unfortunate name this time of, but it's sort of it's reasonable, right? It's sort of what it's what remains after you remove the sun.
Sure. No, that's very, I like the name. It's and I think it's something similar in topology. I don't know.
Yeah, I think that's where it comes from. So the point is that when you're trying to do these more sort of classical assaults on these problems using standard classification results, you run into technical issues that I don't know how to get around. If my ideal is something like a UHF algebra or something like maybe slightly more complicated, which has a complicated ideal structure in the corona algebra. And I'm avoiding that in this result here.
By the way, just very briefly, it's a fun fact, it's nothing deep, but since you mentioned Alexander of topology, which I happen to like very much, we recently observed something absolutely elementary, that if you take any graph and if you take the set of all hereditary subsets in this graph, then it's exactly Alexander of topology for the right order on the set of all your vertices.
Right, yes. Yeah, so this is a very natural, I mean, you have a very natural description of the topology of the primitive ideal space. Yeah. Actually, you also have that with circles. This has been worked out. Okay, so here's a little bit more bad news. So in some cases, we know how to do what you might call an external classification result. So this should remind you of what we talked about when I compared the invariance for the inductive limits with the invariance for the set stable or the Thoms-Winter type of simple C-star algebras. So we have results that say, suppose you have a graph, you have a C-star algebra, and it has the K-theory of a graph algebra. Then you would like to be able to conclude that it is a graph algebra. And we can do this for the simple case is easy, and we can do it with one ideal. Actually, Rasmus Bentman did it in the Kunz-Krieger case. So if you have something that looks like a Kunz-Krieger algebra, not necessarily simple, then on the K-theory, then it is a Kunz-Krieger algebra. So these kinds of results exist, but we don't have a lot of them. So I think if you want to somehow use this result in studying a concrete C-star algebra, then it's more likely that you're going to have to find an isomorphism yourself. Fortunately, there is hope for this, because first of all, this C-star algebra, remember, it's a universal C-star algebra. So it's fairly easy to generate maps out of it. You need to find a representation. You have to find some elements that behave the right way. Right? So if you have a C-star algebra that has the right K-theory, it satisfies these conditions, then perhaps you can find an element, some elements that would satisfy the relations, and then you get for free the map. Now, you want this to be onto, that's, of course, that's sort of up to you by sort of knowing that your C-star algebra is generated by whatever it is you hit. But when you want the map to be injective, you have some very powerful tools that go back to the Kunz-Krieger paper. There's two variants of this. There's the general gauge invariant uniqueness theorem. Suppose that your C-star algebra comes with some circle action, which it sort of has to if it's going to be isomorphic to a graph algebra, because they all do. And suppose that you can make your isomorphism, make this is something that I'm hoping is an isomorphism. Now it's just a homomorphism. I would like this to be injective, and if I can make it so that it commutes with the gauge actions, so the canonical one on the C-star algebra and the homemade one on A, then you can check injectivity just on the projections, which of course is a lot easier. And Szymanski has a result. I haven't written it up very carefully, but it also goes back to the Kunstkrieger paper, that essentially if you want to check injectivity of such a map, you need to check that no projection is killed by it, and then certain unitaries have to be mapped that in the C-star algebra that somehow have to have full spectrum will be mapped to other unitaries with full spectrum. So there's some details I'm glossing over here, but there's some very powerful tools for giving you isomorphism, or at least injectivity, that are extremely useful here. So let's say that somehow you're interested in some C-star algebra and you're asking if it's a graph algebra, then I think this is the most likely way that you're going to be able to do this. And there's examples coming. I mean, the one that I know best is the example of the quantum length spaces that were studied by Hong and Szymanski. These are sort of quantum spaces that you're interested in, and the Waxman-Seubelman sphere. And Hong and Szymanski sort of found some generators, and they found a graph that matched it, and then they could make a map hitting that, and using the gauge invariant uniqueness theorem, that's an isomorphism. So that means that when you're trying to ask whether or not these two C-star algebras are the same, you can transfer the question into the graph algebras, and then you have improved machinery.
I also like to bear witness to that statement. These are very practical theorems. When you want to prove something general, to study an example, I mean, both this theorem, including this bottom one of Wojtek, are very useful, very handy, because you see somehow it's relatively easily verifiable, the assumptions, and then the conclusion is very powerful.
Yeah, and without these results, I mean, as you know, the proofs are tricky, right? You have to work really hard to prove these things. And the reason why it's tricky is that this is a universal C-star algebra, so it's a little bit, you don't know the elements in that a priori. So that's why these are so powerful. Okay, so now I'm getting ready to explain to you what I mean by this matrix picture. So now let's imagine that we have a unital graph algebra. Perhaps we have two unital graph algebras, and we're wondering if they are the same. And I've shown you this sort of general theorem that says that there's a complete invariant, but the complete invariant is a complicated mess of K groups and K0 groups and K1 groups and maps between them. So it's not very nice to try to work directly with the invariant. And so this is where this matrix picture comes in. And actually what I'm showing you here is a part of the proof of this result. We prove it this way. So it's sort of a step back from the glossy classification result, that this is how we prove it. And this is also where we draw on ideas that come from symbolic dynamics. So suppose that I have a graph with finitely many vertices. Then I want to clean it up before I start working on it. I would like to say that if I have a regular vertex, which is not a source, then it supports a loop. So I don't like regular vertices that don't have a loop sitting on them. I also would like to say that if I have an infinite emitter, it emits only with infinite multiplicity. So I don't like an infinite emitter that emits infinitely to one vertex and finitely to another vertex. This
like a breaking vertex.
This creates all kinds of problems for the breaking vertex theory, and somehow you can deal with this, but I'd rather not, right? So that's also what this has to do with. Then the next one looks a little bit strange. Suppose that I have a vertex that has two paths back to itself. This is somehow the generic case. So I can start in my vertex, and there's a way of leaving it and coming back to it without visiting it again. And actually there's two different ways of doing this. Then this is more or less the same as saying that that the underlying spectrum is not countable. That's essentially what I'm asking here. Then I'm asking that the number of regular vertices in the connected component here has to be at least 3, and also it has to be at least 2 bigger than it could have been. And what I mean by that is that when you compute the K-theory, this is some sort of co-kernel, right? So this is a finitely generated abelian group, so it has a number of generators. And the number of generators is the smallest way you can represent this particular K-theory in a matrix. And what I'm asking is that it's slightly bigger than that. So these weird conditions I've stolen directly from the work of Boyle and Huang, where they were used to classify shift of finite type, reducible shift of finite type up to flow equivalence. And then also I would like to have only one regular source. So, I mean, that's just me asking, you know, can I get such a graph? And it turns out that that's possible. So there's a way of taking any graph that gives a unital graph algebra and changing it without changing the underlying graph algebras. And so this is the idea of these moves.
But is your change equivariant or not?
Can I postpone answering that question? So one of them is going to be very equivariant and one less so. And I would like to discuss that in a second.
Okay,
but,
no worries.
So the first thing is also, it comes directly from symbolic dynamics, except we have to amend it a little bit to work with sinks and sources and infinite emitters and so on. That's the idea of an outsplit. And the idea of an outsplit is you have a situation where you have a certain vertex that you want to work with, and you take that vertex and you take the outgoing edges and you put them in piles. So I take this out, I take the vertex that's a star on the left-hand side, and I take the outgoing edges, there's a loop and there's infinitely many across. I take, from the infinitely many across, I take one and I take the loop and I put it on the top. And I take the infinitely many that are left and I put them at the bottom. And then I sort of distribute the choice of my outgoing edges in this way. You can see I get this loop, which is sort of, you have to deal with this in a special way because you're also going to have to worry about what happens to the incoming edges. Well, the incoming edges will be duplicated. So I duplicate the incoming edges and I distribute the outgoing edges. So this is a well-known, this goes back to the work of Williams in the classification problem for shift of finite type up to conjugacy, which is the most sort of natural notion of isomorphism. And Williams proved that outsplitting and insplitting, which is sort of the dual notion, which I'm not talking about here for reasons that will become obvious, that they somehow generate conjugacy, isomorphism commuting with the shift. So so this I do to my graph, and there's various rules that saying you're not allowed to, first of all, you need some edges, right? So I'm not allowed to outsplit sink. Also, if I have infinitely many, then one of my piles needs to be infinite, but there can only be one of them that has infinitely many edges. And then an old paper by Bates and Pass, they prove that then if you do this to your graph, then the C-star algebras will be isomorphic on the nose. And actually, they will also send the diagonal to the diagonal. And actually, they will also commute with the gauge action now you asked about. So this is one thing that I would like to do to my graph. Here's another thing that I would like to do to my graph. This is a little bit less directly from symbolic dynamics. It says, suppose that you have a vertex which does not support a loop. So there's no loop on that vertex. Then you can remove it. And what you then do is that you take the indirect paths and you make them into direct paths. So you can see I have this star vertex which has no loop, so I want to remove it. Then I will say, okay, there's used to be 1, 2 edge like this. This is made into one edge. 1, 2 is made into one edge. 1, 2 is made into one edge. And then you actually need to keep sort of a vestige of the original star as a source. So that has to sit on as a source. Then you can prove that the C-star algebras are isomorphic again on the nose, which is important for me, and the diagonal will be sent to the diagonal, but this time this will not commute with the gauge action. So this is an issue that we need to talk about. So I don't know, I'll see if I could, I wanted to show you something on my iPad where I draw something.
Sorry, may I ask you a question?
Roberto has a question.
Yes.
In this case, and also the one in the previous page, is this isomorphism explicit, concrete?
Yes, yes, they are. These are very concrete isomorphisms where you can describe them by sending generators to generators in extremely concrete ways. That's not always the case. And so we'll come to some ways of changing the graph that will change the that will not change the C-star algebra, but they're going to be isomorphic for sort of abstract reasons rather than concrete reasons. But the two that I'm showing you here are extremely concrete.
Can you give us a hint about how these are, how they look like?
The maps, yeah. So I mean, so essentially, you know, you have before and after you do these outsplits, you if you do the outsplitting, which I think is the one that I can do best, is that you sort of take the outgoing edges and you distribute them into some. They now sit on different vertices, and then you duplicate the incoming edges. You need to come up with some sort of system for giving these names that I don't think I can do off the top of my head. But then the map that we're going to use is going to be like a sliding block code of length 2 in symbolic dynamics, that you somehow the two let's see, I used to have an edge, and I mean, so now I've sort of taken the incoming edges and I split it up into two incoming edges, that because they had this duplication. And then essentially the map that I'm going to define and then prove is an isomorphism using the gauge invariant uniqueness theorem will do something like it takes a word of length 2 and in the outsplit setting and sent it to a sum of some words of length 2 in the other one. So I don't know. I mean, I'm not being very concrete here, but let me say where you read this very well. There's a paper of Ruiz and Tomford about Levitt path algebras, where they show how you can do these moves on Levitt path algebras. And this is the nicest way that I've seen it explained also for C-star algebras. So I'm not sure I can remember exactly the reference for that, but I'll send it to you if you want to see, because it's very pretty, but it's also tricky. So I couldn't, I cannot reproduce it. The other one I think is a little bit simpler, because I will just take, how does it go? I will just somehow you need to use this source to get the map, and in order to use the gauge invariant uniqueness theorem, you're going to have to change the grading on. You have to use a different gauge action than the one that's natural in the target. And that's also the reason why these are not invariant in the more restrictive sense. Okay, let me move on. I'll show you. I'll give you a proper reference for this. Actually, I went through them in a course that I gave once, but it's sort of messy, but it's completely concrete. Okay, now let me see if I can make this work, that I change and show you my iPad. I'm not 100% sure this will work, but so can you see? Yeah.
Yes.
You see this? So this I just wanted to give you an idea of how this gonna work. And so I drew this graph. This has there's an infinite emitter on the top, and you can see it breaks various rules that I'm trying to impose. First of all, this vertex here, it is an infinite emitter because it emits infinitely in a loop back to itself, but it's also a finite emitter, and I want to outlaw that. So what I'm going to do is that I'm going to outsplit that vertex. So I will take this vertex and I will replace it by two vertices, and I will put the loops over here, and I will put the vertex down like this. Then I go like this, and then the rule is that because I also have these loops, they are simultaneously incoming and outgoing. So I need to duplicate them as well. So there's also infinitely many like this. So this is an outsplitting, and it now has the property that the unique infinite emitter is only emitting infinitely. So that's good. But you can see that now, I'll change to another color then.
But why when you duplicate these loops, you go from left to right, not from right to left? What's the rule?
So the rule is that I duplicate the incoming edges and I distribute the outgoing edges. So the outgoing, so I took the downward arrow and I put that to the right, and I took the loop and I put that to the left. But I also need to duplicate the loops because they are also incoming edges. So when they go out,
they go to the right. I see.
They have to start in the same place, but they end up in the other copy. Yeah. But now I have this vertex over here, which I circled in red. That does not satisfy the condition of that's a regular vertex which does not support a loop. So I need to get rid of that. But I can use this was a, I should change color back, sorry. This was orange. So this is an outsplit. And now I can do in red, I can do an R plus, where I just sort of remove this like this, and I have this and that. And then I also get the R plus move tells me to take an extra source and put that in. Okay, so this is better, but still I have down here, I have these vertices. Now I'll need another color again. So there's also something wrong with this vertex because it is regular and it does not support a loop. So what I can do is R plus again. I mean, this sort of gets old, so I'm not gonna do everything, but then I do an R plus again. So I just take this vertex over here and I remove it because it doesn't support a loop. So when I remove it, now there's a loop sitting on the leftmost one. I have to put in an extra source, and I have this situation like this. It's still not okay because the rule is that if I have a vertex that supports more than one path back to itself, then the connected component needs to be big, not too small, right? So the one that I have down here, that's fine because it only has one path back to itself. But the one that I have up here is not fine because it has infinitely many paths in particular too. So I have to make that bigger, and I would do that by another outsplitting. So I hope you can sort of see that there's a way of using the two moves to change my graph in sort of controlled way without changing the Caesar algebra, but where I sort of obtain a nicer underlying graph. So let me go back to my slides here. So what I'm claiming is that there's an algorithm for doing this, right? So if I have any graph with finitely many vertices, then I can change it into another graph, which is in canonical form, using only these two moves. And in the same way, or their inverses, because I mean, you might, for instance, I would get a bunch of sources, and I have a rule saying that there should only be one source. But I can just do the opposite of an outsplit, which is called an out amalgamation, and I can join all these sources to one. So there's sort of systematic ways of cleaning this up. And actually what you can then do is that you can not only clean them up so that they become canonical separately. If you have two, you can make them into the same shape. So what you should imagine is that I have two graphs, right? I want to figure out whether or not they're isomorphic. Of course, for them to be isomorphic, they would have to have the same number of gauge invariant ideals, which is the same as saying they would have to have the same number of connected components. Now, these connected components would also have to have the same type. So you would have some connected components that just contain a single point, which is a sink or an infinite emitter. It could also have a single point which supports just a single circle, but it could also have a point which supports more than one path back to itself. And then the rule says that that has to be big. So essentially, the rule of having canonical form means that all the components are either made very small, one by one, or they're made big. And since I can make them as big as I like, if I have two of them and I want to classify them, I can make them to be exactly equally big, right? Because so when I've sorted one of them out and I've sorted the other one out, then probably one has fewer vertices than the other. Then I just inflate the smaller one until they have the same size. So what I can do is I can take my graphs, and in a systematic way, it's algorithmic in the sense that it doesn't really matter what order you do. You can sort of do a naive, what's it called? The word escapes me. An algorithm that sort of doesn't look ahead. This is called. Okay, I'm not remembering what this has a computer science name. I mean, sort of, it just means
greedy.
Greedy. Thank you. It's a greedy algorithm that I just.
It wasn't me, just Matthew Dawes.
Whenever there's a problem, you just take the next problem and you keep solving that until you're out of problems. That will work here. And then the point is that now I can take the two graphs and I can actually either this procedure will tell me that these are definitely not isomorphic, or they will give me two graphs that have the same shape. And essentially, you can think of them now as the regular adjacency matrices that you get by just deleting the sinks and the infinite emitters. They will be, if you like, sort of upper triangular matrices of the same size. And since they're now upper triangular matrices of the same size, you can talk about whether or not it's possible to intertwine them with square matrices. So there's a little snag here that my matrices have been made by deleting some rows and then transposing. So these are matrices that are not square necessarily, they're rectangular. They're taller than they're wide. So the U and the V that I'm talking about are not necessarily of the same size, but they are square, right? Because the BE and the BF, they are the same size. So since they're square, it makes sense to ask if they're invertible, and they also have to be block diagonal matrices in the same sense that the original graphs were. So essentially what happens here is that you can take your graph will have some various connected components. These connected components will communicate in various ways. This tells you that you can place everything in a matrix that is, say, an upper triangular matrix, and then some of the upper triangular blocks, so all the ones below the diagonal will have to be zero, otherwise it's not upper triangular. But on the top as well, some of the blocks will have to be zero. If there's no way of going from this component to that component, then the whole block has to be zero. And so that's what I mean by GL in this little plus symbol here. It has to be an upper triangular invertible integer matrix that is zero the right places. And so the nice result here is that now everything is a matrix question, right? So when I put things in my canonical form, you've noticed that I made some of the components slightly bigger than they had to be. And then the theorem that essentially goes back to symbolic dynamics from Boyle and Huang then shows that you don't have to increase the size anymore. when you have that size, then if you have the same system, that's because you have the U and V that are exactly of that size. So you can see I've sort of tamed the problem instead of looking at sort of intertwining with matrices of general size, they have to be of a certain size that is slightly bigger than it had to be, but still something I can control. So this is actually how we prove the theorem. So when we prove that you have stable classification, then essentially we prove that if the K groups are isomorphic, then you can lift that to a GL equivalence in this setting. Now, by the work of Boyle and Steinberg, which goes back to the work of Grünewald and Siegel, this is decidable, but I have to warn you that this is not nicely decidable, because essentially you can see this problem that I'm stating, it's linear. I mean, if I have a concrete BE and BF, right? So now let's say I have two graphs. I'm wondering if the graph C-star algebras are isomorphic. I cleaned them up and put them in the same size, so they're sufficiently big. And now the theorem says that the C-star algebras are stably isomorphic if and only if I can find the U and V. Now, the U and V, I can just, say this is a matrix with integer entries. I call them U11, U12, and so on. Some of them have to be 0. And then now the way that I've written it up, you can see this is a linear problem. So it's integer linear, but you can definitely figure out if there's solutions of U's and V's. But I want to know that these represent invertible matrices, right? And usually you would check that by looking at the determinant. You want this to be plus or minus 1. And then this is no longer something that you can easily compute, because you're sort of if you're just going that way naively, you're in the territory of Hilbert's 10th problem. And so you cannot, this is known to not be decidable, but actually there's a way around this using this Grünewald-Siegel theorem that says that this is invertible. Now, if you're lucky, which you are in the case of the quantum length spaces of Hong and Szymanski, then all the diagonal entries are 1 by 1. That's because actually the C-star algebra they have is a type 1 C-star algebra. So there's no vertex with more than one loop back to itself. And then it just becomes the linear problem, and you can actually write a program for looking for these, which I've done, and this is useful for all kinds of things. But in general, I think you're going to have to use a little bit of human ingenuity to figure out if there are these. I mean, in practice, this is my experience that this is something that can be done, but there's no sort of machine for it. And you can also do an on-the-nose result. Then you just need to keep track of the class of the unit. And the class of the unit, from the way that we put things in standard form, is essentially given by what emanates from the single source that I have. So the data that lives of things coming out of the source, that is what you need to get an on-the-nose isomorphism. So this is a much better way of answering these kinds of questions, because you are now away from having to look at all these finitely generated groups, and you can just look for matrices that satisfy certain conditions. So, okay, so how can what is my time frame now, Piotr?
Well, you have 6 minutes left, but...
Perfect. I mean, I'll just show you sort of, because now I'm done with the user guide discussion, and now I just want to put this in a context and mention some more interesting, some current problems that I don't know the answer to. And so, of course, that may not be what you're looking for, but the next thing that I would like to discuss is that suppose that you care about the canonical data in the graph algebra. So suppose that when you had your C-star algebra that you care about for some reason, when you proved that it was isomorphic to a graph algebra, you proved it in a way that either preserved the diagonal or it preserved the gauge action. So somehow you have reason to care about the gauge action or the diagonal. So you can ask 8 questions. And you can sort of, and I have notation for that, but I don't think we, okay, let me just quickly show you that notation. So,
sorry, I know it's embarrassing, but can you remind me the diagonal? I just forgot.
Yeah, so the diagonal is what you get by looking at S alpha star. So these are sort of balanced elements that somehow, and they will all commute because of the relations. Okay. So that is a canonical part of the data in a graph algebra.
Yeah, it was, you defined it at the beginning. I just
yes. So so I want to define 8 kinds of isomorphisms, and I have sort of 3 choices. The first choice is, do you want it to be on the nose or stably so? The second choice is, do you want the isomorphism to commute with the gauge action or not? And the third choice is, do you want it to preserve the diagonal or not? And so in order to have language for this, I call this X, Y, Z isomorphism, where X is the bit that is set if you want an on-the-nose isomorphism. Y is the bit that is set if you want a a gauge invariant isomorphism, and Z is the one that you need to preserve the diagonal. So let's first talk about the on-the-nose isomorphism. So that's the 1 Y set. So there's 4 of those, right? So if it commutes with the gauge action, then I put a 1 in the Y position. If it sends the diagonal to the diagonal, I put a 1 in the Z condition. So I have these choices. That's sort of obvious. But when I'm doing the next one, where I'm only doing stable isomorphism, there's sort of a choice involved here, because now I have to tell you how I extend these objects to the stabilizations. And I'm going to do it in the following way. So, I mean, so a 0YZ isomorphism, that's just a stable isomorphism. I will say that it preserves the gauge action if it preserves the gauge action tensor the identity on the compact. So, so sort of the trivial extension. That's to many people, I think that's a surprising choice, because there's sort of a regular choice of doing this that comes up in Takai duality, which is somehow perhaps a more natural choice from the perspective of cross products and these kinds of things. But it turns out to be the right thing for what I want to do here.
You could also take it sort of diagonal, because you also have gauge action on the compacts, but you don't want to do it.
So, I mean, so the compacts is a graph algebra, right? I didn't show you, but that's just a long path. And then as a graph algebra, it comes with a canonical gauge action, which is not the identity.
Yeah.
So I'm sort of choosing something that doesn't come from the compacts as a graph algebra, which is perhaps weird, but it works best for what I want to do here. You can sort of do both. Extending the diagonal is easier. You just take the canonical diagonal down the real diagonal of the compact operators. And then, so now I have these 8 notions, and you can sort of put them in this little cube here. And it's clear that if you have something with a 1, that, I mean, you have an isomorphism with a 1 somewhere, that's stronger than having an isomorphism with a 0 somewhere. It's not obvious that these notions are different, and it actually took us a long time to find all the examples, but I know now that these are different concepts. And I'm asking the question, which of these are decidable? The main reason for doing this, and I'm sort of having to break my vow of talking about symbolic dynamics, that the one that's called 011 corresponds in the Kunstkrieger case to what's called strong shift equivalence. And it's important open question if that is decidable. And it's sort of my crazy ambition for this project to say something about that by sort of going from both sides using C-star algebras, but we're definitely not there yet. So I don't know if the 011 concept is decidable, but I know that everything in the bottom layer is decidable almost. So the result that I just showed you was that 0, 0, 0, that just means stable isomorphism, no extra structure. That is decidable by the result I already showed you. 1, 0, 0 is the on-the-nose isomorphism, no extra structure, and that is also decidable by the results I just showed you. If I have, oops, there's a typo. If I have no infinite emitters, I can put 0, 0, 1. So this is supposed to be a 1 here. And then you ask for SL matrices rather than GL matrices. That just means that the diagonal matrices have to have determinant +1. I know this in the Kunz-Krieger case because it relates to flow equivalence. But if I have infinite emitters, I actually don't know. And you can do the same with unital isomorphism. So that I have. And then the final statement is that actually we can also do the 0, 1, 0 case. So we managed to prove that in a sense, this has been done a long time ago in the primitive case and work of Bradley and Kishimoto. But it turns out that the 0, 1, 0 equivalence, which means so a stable isomorphism that commutes with the gauge action, this you can recast as a question about dimension groups. And this is a famous result of Krieger that says that if you want to understand shift equivalence of shift of finite types, you can recast that by looking at a certain dimension group. And that's the dimension group that I showed you at the very beginning. This is one that comes from a stationary system. But you look not only at that, but also at a certain shift map, which is natural here. And then, so you can sort of recast this question as a question in dimension groups. And then it turns out to be, it's a long story. I don't have time to explain how this is done. But then by more classical work of Kim and Rausch, this is actually decidable. So you can do that. But that's the end of what I know of decidability. So let me just I'm going to skip this very quickly. I want to show you one slide at the very end. Is that okay? So you can do more moves, right? So you can do, there's something called an S move, an I minus move, I plus move, a C plus move. This is the famous Kunstspice, something called the P plus move, blah, blah, blah. So there's various things that you can do through the graph that don't change the stable isomorphism class of the graph. And some of these moves will be better than that. Outsplitting, the one that we looked at, preserves everything. A special kind of in-splitting preserves everything, but the general kind of in-splitting does not. And you can sort of put in these moves that are have various kinds of nice properties. We came up with something that we're calling the Krieger move. I haven't check this with anybody, not Wolfgang, but the idea is that that's not really a geometric move like the other one. It's something that is of the same nature as the result that I just showed you. It sort of compares dimension groups. At least it's decidable, but actually we don't know if it's invariant the way that I'm stating in general. And then we have this conjecture that all these 8 types of equivalence are generated by the moves that respect it. So what I mean by that, and this is the slide I want to show you, is that we can talk about 0, 0, 0 equivalence. This we actually know is generated by the moves, right? So all these moves will respect the 0, 0, 0 equivalence, and if you have 2 0, 0, 0 equivalent systems, you can go from one to the other using these moves. And I can do the same with there's a typo here. I can do the same down here, the unital case. I can do that's where I need an equal sign. But then in all the remaining 6 cases, we still don't know. So so this is open, right? So I'm not saying that you should start using this because I don't know if it's true. But if we manage to prove this, this would also be a very big help in order to work directly with these kinds of C-star algebras, because then that sort of tells you if you have 2 C-star algebras and you care about some sort of one of these 8 kinds of isomorphism, then it tells you the way that you can change the graph without changing the C-star algebra. But as I said, this is conjectural, so I'm working with Efren Ruiz on that.
But this is very natural. And by the way, I very much like the title of this slide, partial general.
Yeah, I mean,
sweet and sour.
yes. So I mean, general. So in various cases, actually, so we we can do it in the classical case of a simple Kunst-Krieger case, Kunst-Krieger algebra. These statements, the 8 statements that I put up here, we know that they're true. We can also do, there's something called amplified graphs. We can do that case too. So these are specialized results that are nicer. But of course, it's cheating a little bit because in that setting we have some very strong results that I can just appeal to. So I don't know if that's honestly evidence one way or the other. It's something that I would like very much to be true, but there's lots of work to do. Especially the infinite emitters is a big problem here. Let me stop here.
Okay, thank you very much. So I'm virtually clapping hands. So you see my clapping hands. This is a wonderful talk, and maybe now there are still some questions. I hope there are still some questions, so please fire at will. Yeah, Guillermo, please go ahead. If you have a question, just ask.
You're muted. So.
Here, I was muted.
Yes.
Yeah, no, so I had the vague impression that this filter K-theory business and the classification of sister algebras with a given finite prime primitive spectrum had an interpretation in terms of Bavarian K-theory, where somehow the finite space X was brought to play, like a KK super X. Is there such a thing?
I mean, there is a very interesting and difficult issue about the UCT in this setting. So I think perhaps that's what you have in mind. So there's this very general result by Kirchberg, which says that if you have two not necessarily simple purely infinite C-star algebras that are KK equivalent in a way that somehow preserves the ideal lattice, then the C-star algebras will be isomorphic. So and then the question is, how can you go from K-theory to that? And that turns out to be quite complicated, because the more general kind of filtered K-theory that you would need here doesn't have nice homological properties. So this was mainly worked out in work of Meyer and Nest, where they show that various kinds of ideal lattices will lead to situations where this filtered K-theory doesn't work, where you have to, and for sort of homological reasons, that there's the projective dimension of these objects is too high for you to get a UCT. So there's a sort of a huge business around this, which I've swept under the rug here, because we can actually get by with this more simple-minded invariant in this situation. But it's also quite likely that our working conjecture in general for the not necessarily unital C-star algebra fails for these kinds of reasons. But there's still no counterexamples. So it's actually some very nice positive results that somehow go through these results of Meyer, Nest, and Bentman and Köhler also for doing this. So there's a whole, the general question of how you go from K-theory to KK theory, even for a purely infinite C-star algebra with finitely many ideals, is a very complicated question that I'm avoiding here. So.
Okay, anybody else?
Can I continue the question of Cortinius?
Sure.
So if we have a filtration on a C-star algebra, then we have a spectral sequence, the Choquet spectral sequence. How, in this case, this spectral sequence splits into 6-term exact sequences?
I'm actually looking at Richard. So I think he's your guy. Sorry. So
well, that's this filtered KK, right?
Yeah. Yeah, but you don't like that so much, right?
So, no, though you don't get a nice spectral sequence.
Right.
It's Z2 graded, so it doesn't quite work this way. Remember, it is Z2 graded and 6-term. There's some kind of 6-term exact sequences, right? So you don't really get a spectral sequence for that.
Okay. Okay. So second question. Maybe stupid question. How many graphs in canonical form are C-star isomorphic or stably so?
Yeah, I think, I mean, so we did actually, before we had the result, we did these naive experiments where we took, I mean, first of all, you can define these matrices that I showed you. They all have, I mean, some of them have multiplicity 2 and so on, but actually it's fairly easy to see that any graph algebra can be given by a matrix that has multiplicities 0, 1, or infinity, right? So infinity you sort of have to deal with, but if you have 2, you can sort of outsplit, so you get down to 1. And then we looked at the universe of all small matrices that had entries 0, 1, infinity, and wrote a program to sort of sort them out into groups, and they very often become the same. I mean, I don't have a precise answer to your question, but just because you have 2 graphs that are in canonical form, it's not. The canonical form is far from unique. You have many, and essentially you can sort of see that in the GL or SL notation, because essentially what that tells you, and this also comes from symbolic dynamics, is that suppose you have an adjacency matrix, then you can add rows to rows and rows to rows or columns to columns if you're careful not to destroy the block structure. Then you can do this without changing the C-star algebra. So I think, I mean, there's really nothing like a canonical choice of a canonical form, if that's what you're.
What about row finite case? Is it true that is there a chance that there is a finitely many representatives in canonical form? Or
no,
it could be infinite?
I mean, the canonical form doesn't really have anything to do with being unique. It's just,
yes,
it's just
maybe it's a bad name.
How much non-unique?
No,
it's very non-unique, I would say.
Very, okay.
Yes, because
so typically there are infinite number of canonical presentations.
Yes, you can always just take an edge and expand it and work.
It could be unbounded. I mean, so the entries that you get, I think this is what Gunnar has in mind. If the entries, you can sort of keep adding. So within the same class, you can get an unbounded matrices that represent this.
Okay, thank you.
So I mean, in a sense, maybe canonical form is not a good word. Too late to change that now. Sorry. Okay. But it's not canonical. It's sort of it's cleaned up.
Mm-hmm.
So what about if you assume it's the smallest size canonical? How much choice is there?
Yeah, I think. Yeah. So you're saying somehow fewest possible vertices, fewest possible edges.
Precisely.
Yeah.
Let's say fewest possible vertices. Fix something, right?
Yeah, I don't think that helps but then you'd also have to make the number of edges small, because you can always increase that. I've never thought about that. So I would be pessimistic about making that work, but I cannot disprove it. So
could be something told about minimal canonical form.
Yeah, some. I think this is what Richard is suggesting, that
yes,
somehow you say that
yeah.
the number. I mean, I think automatically, if you make the number of vertices as small as possible, then I think that also takes care of the number of edges as small as possible. That also takes care of the edges, so the vertices. Sorry, but I'm not 100% sure.
So there's an analog.
Because, I mean, I understand why you ask this, because that would also be a way of getting an algorithm, right? Because now you just put it in that form and you compare. And so if that was possible, that would definitely be stronger than what we have.
So I'm only suggesting that there is an analogical program in algebraic geometry, in birational geometry, a program of minimal models.
I see. Okay.
So maybe it could be the beginning of some interesting scientific program.
I'll definitely think about it. That's a very interesting idea that somehow never occurred to me. So, thank you.
Okay, Tomek is done. Anybody else?
What about embeddings? Not isomorphisms, but embeddings.
I mean, that's a touchy issue, because so the short answer is I know very little. I would very much like to know something, because every graph C-star algebra is an inductive limit of unitary graph C-star algebras. So if I could somehow, I mean, this is what is done in the Elliott program. It's definitely in the units in the traditional case of inductive limits, that you have existence and uniqueness but you need it for homomorphisms, not isomorphisms. And I don't know how to do it. So the problem is that I'm not even sure how to make sense of this sort of move calculus for maps between graphs. But it could very well exist. I just don't know how to do it. So the answer to that is that I wish I knew. So.
All right.
Okay, anybody else? Any more questions, comments? I'm scanning through everybody, but nobody raises a hand. So in this case, let me ask you some questions, if I may. Sorry. So first question is actually only tangentially related to your talk, but in fact, this appeared when I was discussing via email the question of how to recognize whether a given C-star algebra is a graph C-star algebra. So that's exactly your talk. And then when we were discussing it, it occurred to me that you might somehow lift this question to the following question. How can you recognize whether a given star homomorphism between graph C-star algebras is of, so to say, graphy nature? Okay, and let me instead of making this term more precise, let me pose you a very concrete mathematical question. You see, ages ago with Wojtek Szymański, I mean, Wojtek did it in a joint paper of ours, we proved that when we take the pullback of two Teplitz algebras, which of course are graph C-star algebras, over the circle C-star algebra, which is again a graph C-star algebra. Well, if you do it in a regular way via the symbol map, then what you get is the celebrated Podlesh equatorial quantum sphere, right? This is like gluing two quantum disks over the equator. But for topological geometrical reasons, we wanted a different pullback structure. We wanted to have one morphism to be the symbol map, but the other sort of to be conjugate. So we would map the partial isometry of the Teplitz algebra, sorry, the isometry of the Teplitz algebra to inverse of the generating unitary of the circle. And when Wojtek proved using K-theory, I mean, positive cone, I suppose, if I remember correctly, he proved that these two sister algebras, one of a Podleś quantum sphere, equatorial Podleś quantum sphere, and one what we baptized as the mirror quantum sphere, because sort of this was like a mirror reflection of one of the disks, that they are not even stably isomorphic. And so this is a very subtle effect, because you don't do something crazy. You make a very natural and what would appear to be a minor change, and then you completely go out of the realm of graph sister algebras. So how would you answer the following question? How to recognize when, well, because when you want to define a pullback, the pullback is given by a pair of homomorphisms that end at one and the same target. So what would be a criterion, at least sufficient, to guarantee that my homomorphisms are of such a nature that when I take the pullback with respect to this homomorphism, I will end up again in a graph sister algebra? What would be a criterion? And obviously, what I just gave you would be something failing this criterion. But I think this might be an interesting problem to resolve.
I agree. That sounds very interesting. I mean, I'm not even sure this is an answer to your question, but of course there's a similar question that has to do with isomorphisms on a graph sitter algebra, that you're asking if they somehow come from moves, for instance.
Yeah, for instance,
yes. This is one of the problems that we have in order to deal with infinite emitters, is that we don't know. I mean, you could take something with infinite emitters and some K1 or something like that, and there's a situation, I'm not exactly remembering precisely what it is, we don't know, but there's various kinds of isomorphisms at the level, automorphisms at the level of the K-theory. We don't know if we can make it with moves or not. So that's the same of saying that, I mean, this isomorphism, it comes from a graph operation or something, graphy and whatever that means. So the systematic knowledge we have about this is sort of limited. And what we know comes from symbolic dynamics, in the sense that there's some fundamental work by Boyle that says that various isomorphisms on the Bowen-Franks invariant can be realized as moves, and you can somehow transfer that to sister algebras. But
yep, okay, I'm very happy with the answer. And now a sort of general question: how much of what you told us today is or would be or conjecturally is valid for Leavitt path algebras?
I don't think I dare to have any guess from that, but I can tell you what is known,
okay,
or rather what's not known, because I mean, so of all the moves that I showed you, I mean, I went very quickly over the last one, but the Kunz splice is a way of changing the graph that goes back to a very early paper by Kunz. And what essentially, when this was done, it was unclear if these two sister algebras would be isomorphic. This was then handled by Rørdam, who proved they would be isomorphic using classification and K theory and so on. So this is an example, also returning to Roberto's question, that this is an example of an isomorphism that's not concrete. It's not given by sending generators to generators. We sort of know it exists. And this is the big open question for Leavitt path algebras. If you can do this, I mean, when you do a Kunz splice, will the Leavitt path algebra have to be the same or not? We don't know.
Excellent.
And I think until we work that out, I mean, we're sort of stuck. But of course, you can try to do some of the other questions. And I've been talking to Ruspe Hasrat, who knows a lot about these like graded isomorphisms. And I think there's a tendency that, again, we don't know this, right? But I would be a little bit more optimistic about proving sort of generation by moves if you put in a little bit more structure for the levered path algebras.
Mm-hmm. Okay.
But that's just guessing. I mean, it hasn't been worked out.
Okay, thank you very much. And I have one final, this is now very elementary question. It seems that this decidability was very important for you in your talk, right? You like these results. Although I guess we all have a certain feeling of what decidability means. Could you give like a precise definition of this is decidable, this is not? How exactly do you define that something is decidable?
Oh, I mean, to me, it would just be, it's some sort of algorithm that terminates, and I mean that I know will terminate with the answer either they're the same.
Okay.
And this is the notion that's used in this work of Grunewald and Siegel that we're. But then, of course, you need to worry about how fast these are. But essentially, it's like a Turing machine that you definitely know will terminate with the answer.
That's exactly what I wanted to hear. Okay, perfect. So if there are no other questions, let us thank Søren again for an extremely beautiful talk and a very useful user guide. Like it's like the Hitchhiker's Guide to the Galaxy, right?
Yeah, I mean, let me say, of course, that if anybody is wondering about these things, I mean, ask me or ask somebody who works. I mean, we're all very excited to see this used in any setting. So we will be very happy to help you. Even though I try to give you user's guide, you can also just ask. So.
And you're very smart, giving a very big set of collaborators. So there are many people to help you with answering questions.
Yeah, I mean, I think I've successfully tricked a lot of people into working on this.
Yeah. So thank you very much. Thanks again. Here I'm clapping my hands again, and let me make the following announcements. Now we have a semester break. So this was the last talk of a semester. And Søren, you worked some magic here. Can you believe it? That it's the first time ever that you brought all organizers of a seminar together. It was the first time that all the organizers were present.
Yeah, it's also because it's very difficult for me to. So I have to watch them later.
Yeah, but I'm very happy about it. And of course, you also broke our barrier. You topped at 48 participants. So you vastly improved Christian Vogt, who had 32. So this was great. I hope this will be a nice tendency. So definitely a very, very good job. And thank you very much for this. We resume on 24th of February. And the first talk will be by Andrzej Sitasz. Then on 17th of March, we will have a talk by Sergei Neshveyev. And on 31st of March, we'll have a talk by Guillermo Cortinas. So that's what is fixed by now. And of course, we are working on far further invitees. But for the time being, that's all we know. So thank you very much for the first semester of NATO, North Atlantic Noncommutative Geometry Seminar. And I hope to see you all and other people in the next semester. So I stop recording right now. But if I might request my fellow co-organizers to stay for a minute with me, it would be great. So the official part ends right now.